Hello everyone, I'm Yafeng Pan from Department of Clinical Neuroscience, Karolinska Institute, Sweden. Today I'm going to be presenting some recent work on teacher-student interactions from an educational neuroscience perspective. So data were collected when I did my PhD at University Libre de Brussels with Professor Philippe Penio, who's a leading expert in sleep and learning. The title of my talk is Interpersonal Brain Synchronization with Instructor Compensates for Learners' Sleep Deprivation in Interactive Learning. Much of human learning emerges as a result of interaction with others. Such social interactive learning is critical for a range of human activities, from basic survival behaviors to the mastering of complex cultural tasks. As Greek philosophers highlighted, more than 2,000 years ago, verbal turn-taking interactions are powerful means of education and pedagogical practice, the so-called Socrates dialogue. Today, despite the rise of individual approaches to learning, such as e-learning and multimedia, learning through social interaction still plays a vital role in the daily lives of many people. Examples of social interactive learning span from infancy to adulthood, including learning of new rules, the acquisition of fine motor skills, or teacher-student classroom teaching and learning. Of particular interest, how the human brain supports such social interactive learning. In spite of the surge in interest in the neural mechanisms of social learning, important gaps in our understanding remains. First, although social learning involves by definition at least two agents, for example, one learner and one instructor, conventional neuroscientific approaches to social learning have mostly focused on the activity of single brains without exploring the dependencies among activities in two or more interacting brains. Second, most studies in the field of social interaction have adopted ecologically deprived setups in which natural behavior is strongly constrained. This requires further validation in more naturalistic situations. The study of the brain mechanisms underpinning social behavior is currently undergoing a paradigm shift, moving its focus from single individuals to the real-time interaction among groups of individuals. Recent methodological advances, hyperscanning, allow researchers to measure similar or synchronized neural responses, known as interpersonal brain synchronization, across diets and groups of individuals in a social situation. Whereas single brain studies are useful in localizing brain activity associated with social behaviors, interpersonal brain synchronization can directly assess the dynamic interaction of two or more brains. The hybrid scanning technique, or the measurement of brain activity from multiple individuals simultaneously, can be combined with different neuroimaging modalities, for example, EEG, MEG, fNIRS, and fMRI. Although this development has opened new opportunities to study how interpersonal neural responses shape memories and behaviors through learning, there have been few direct links to the rich field of learning science, including that focusing on social interactive learning. We explicitly tested the link between interpersonal brain synchronization and interactive learning in our previous work. We recorded brain activity from learner-instructor dyads using functional near-infrared spectroscopy, fNIRS, during the acquisition of a music song. In the study, the teacher was instructed to teach a four-phrase music song to a student, during which their frontal temporal parietal regions, which hold strong relevance for social interactions, were monitored and recorded simultaneously. Functional near-infrared spectroscopy is a novel, non-invasive neuroimaging technique. It can capture blood oxygenation and hemodynamic change of the human cerebral cortex. Importantly, it allows the measurement of brain activity from multiple individuals simultaneously. We made four key observations. First, during the interactive learning task, brain activity recorded from the bilateral inferior frontal cortex synchronized across the learner and the instructor. Second, such interpersonal brain synchronization was observed in particular when the learner was observing the instructor's vocal behavior, and when the learning experience entailed a turn-taking and more active mode of interaction, as evidenced by a video coding analysis. Third, this specific enhancement of interpersonal brain synchronization predicted learners' behavioral performance. Fourth, granular causality analysis further disclosed that the signal recorded from the instructor's brain better predicted that recorded from the learner's brain than vice versa. A later study tested the similar research question in a real-world classroom. They found that social factors such as perceived closeness are reflected in brain-to-brain synchrony and can predict cognitive outcomes such as students' academic performance. Together, these results indicate that social interactive learning between instructor and learner can be checked by interpersonal brain synchronization. The current project takes a step further by investigating the role of sleep deprivation in interactive learning. Sleep deprivation is known to affect learning abilities and social interaction. Both hold strong relevance for social interactive learning. Insufficient sleep and/or poor sleep quality in children and adults are associated with cognitive dysfunctions, mood changes, and social deficits that may affect learning and academic performance. According to the empathic deficit hypothesis, sleep deprivation affects the ability to recognize and categorize others' emotions and reduces the individual's self-perceived emotional intelligence by affecting the ability to be empathetic towards others. Moreover, sleep deprivation is associated with impaired emotional reactivity and control, both being relevant for sharing others' emotional state and social interaction. In this respect, empathic deficits are probably amongst the main factors that impede social exchange, which eventually have the potential to impede the relation between an instructor and a learner during interactive learning. Notwithstanding, sleep deprivation-related social interaction deficits might to some extent be compensated by recruiting resources beyond those utilized after a normal night of sleep, a compensatory phenomenon usually accompanied by stronger or more extended brain activity. Hence, according to the compensatory recruitment hypothesis, the sleep-deprived brain would show compensatory neural activity that enable relatively preserved behavioral performance, including learning. In this study, we investigated whether and how sleep deprivation that potentially impacts both social interactions and learning abilities modulates interpersonal brain synchronization in interactive learning. Due to the interactive nature of face-to-face learning, we anticipated an interpersonal brain synchronization between instructor and learner. Considering the hypotheses discussed above, interpersonal brain synchronization could be decreased after sleep deprivation due to deficient empathic abilities. Alternatively, enhanced if a compensatory mechanism develops. The latter compensatory hypothesis is inspired by both previous single brain studies and emerging two or more multi-brain findings showing that interpersonal brain synchronization selectively increases in individuals with behavioral social deficits. In a repeated measures crossover counterbalance design, the learners took part in two experimental conditions separated by a 1-week interval counterbalance. Once after a night, uh, once after a night of regular sleep at home, and once after 24 hours of sleep deprivation. Each experimental condition included two behavioral sessions. On day one, participants completed a set of psychological scales and were administered a numerical reasoning test to evaluate their baseline proficiency level. At day four, 3 days later, they participated in the FNIRS hyperscanning experimental session either after a night of regular sleep at home or total sleep deprivation in the laboratory. In this FNIRS hyperscanning experimental session, they had first to complete self-report questionnaires and a numerical reasoning pre-learning assessment. Then the instructor taught numerical reasoning strategies to the learner in a one-on-one interactive manner, while their cortical activity was simultaneously recorded and their interactions videotaped. Immediately after the scanning session, participants were administered a post-learning numerical reasoning assessment. For the sleep deprivation condition, the learners arrived at the laboratory one night before the scanning. We checked their sleepiness and empathy level throughout the whole night. For the regular sleep condition, the learners had regular sleep at home. In the next day morning, the instructor, who always had a regular sleep, came to the laboratory and was scanned via FNIRS with the learner together. In both regular sleep and sleep deprivation conditions, normal rest activity patterns were monitored using actimetry, a wrist-worn device monitoring motor activity, and subjective sleep logs using Stanford sleepiness scale for 3 consecutive days before the FNIRS hyperscanning session. Participants were also specifically instructed to engage in daytime naps and to abstain from alcohol and caffeine during this period, including throughout the sleep deprivation night. On the behavioral level, sleep-deprived learners initially performed below their baseline level, worse than regular sleep learners. But learning improvement was comparable between regular sleep and sleep deprivation conditions after learning with the instructor. Here, X-axis indicates the sleep deprivation pre-learning, sleep deprivation post-learning, regular sleep pre-learning, and regular sleep post-learning conditions, respectively. Y-axis means efficiency level, which was measured as a ratio between accuracy and duration. Accuracy means was defined as the ratio between the correct items and the total number of the items. And duration was defined as the time in seconds necessary to complete the items. Subjective measurements confirm that sleepiness and vigilance parameters were altered, and empathy was also impaired in learners in the sleep deprivation condition. On the neural level, learners and instructors' brain signals were collected simultaneously. After a series of pre-processing, for example, principal, component, special filtering, and correlation-based signal improvement. Interpersonal brain synchronization between learners and instructors was computed using wavelet transform coherence. The wavelet transform coherence ranges between 0 and 1 and can be conceptualized as a localized correlation coefficient in time and frequency space. We observed interpersonal brain synchronization in both sleep deprivation and regular sleep conditions. However, interpersonal brain synchronization within the instructor-learner diets was higher in the sleep deprivation versus regular sleep condition in the left inferior frontal cortex. To further extract meaningful information from multi-dimensional arrays, interpersonal brain synchronization illustrating the unique instructor-learner brain-to-brain network were clustered separately in the sleep deprivation and regular sleep conditions using non-negative matrix factorization. The three-cluster solution was used to find the best fit in the sleep deprivation and regular sleep conditions. We found that clustered interpersonal brain synchronization was correlated with performance improvement only in the sleep deprivation condition. Cluster 2 showed a significant correlation with learning improvement in the sleep deprivation condition. That is, increased in-person brain synchronization in cluster 2 was associated with improvement in numerical reasoning performance in the learner. And note here, cluster 2 in the sleep deprivation condition mostly engaged inferior frontal cortex regions, which echoed our previous findings. And we additionally probed a potential relationship between interpersonal brain synchronization change and empathic deficit in the sleep deprivation condition. Specifically, Pearson correlational analyses were conducted to test the correlations between clustered interpersonal brain synchronization and subjective objective empathic deficits measures. Empathic deficit was defined as a difference empathy value at 9 o'clock a.m. and 9 o'clock p.m. And neither subjective nor objective measurements correlated with clusters 1, 2, 3. Finally, Granger causality analysis revealed biased causality with higher instructor to learner than learner to instructor directionality in brain signal processing, indicating that it was the instructor rather than the learner who led the interactions. Together, these results indicate that sleep deprivation-related learning deficits can to some extent be compensated via interactions with an instructor, as reflected by increased interpersonal brain synchronization and preserved learning ability. It suggests an essential role of the instructor in driving synchrony between teaching and sleep-deprived learning brains during interactions. In the current study, we replicate previous findings showing that social interactions in a naturalistic environment induce synchronous activities in series of mind-related brain areas, including inferior frontal, superior temporal, and temporal parietal regions. Besides validating prior findings, we show that interpersonal brain synchronization and interactive learning are modulated by physiological constraints, such as sleep deprivation. We surmise here that interpersonal brain synchronization might act as a tie through which the instructor continuously entrains the learner to align her behaviors as well as underlying activity in neural networks, facilitating social interaction and information exchange. To successfully achieve interpersonal alignment, both instructors and learners should recruit compensatory neural resources beyond those utilized after a regular night of sleep to keep in sync. In this context, additional enhanced interpersonal brain synchronization eventually supports the instructor-learner interaction to successfully improve the learner's performance. This hypothesis is supported by results from our comparison between interpersonal brain synchronization in the sleep deprivation and regular sleep conditions. As sleep deprivation induced more widespread interpersonal brain synchronization than regular sleep. Moreover, we found a significant association between clustered interpersonal brain synchronization, represented by cluster 2, and learning improvement after sleep deprivation, suggesting functional significance in the interpersonal brain synchronization. Okay. And a major characteristic of our design is that we investigated synchronous brain activity between a learner who was sleep deprived and an instructor who did not receive sleep disruption at all. Granular causality analysis showed that after sleep deprivation, mean causality was significantly larger from the instructor to the learner than the other way around. This suggests that the instructor might play a more important role in social interactive learning than the sleep-deprived learner. As such, dynamic social interactions that are key components for grasping the other's mind would play an important role in sleep-deprived interactive learning. Following sleep deprivation, despite brain activity compensation in the learner, the instructor guided the communication, monitored the learner's responses, and entrained their brain activity with one of the learners. As a final note, I'd like to discuss some future possibilities. First, in this project, we mainly focus on brain-to-brain synchrony in interactive learning between instructor and learner. It would be interesting to explore whether synchrony could track learning in other formats. For example, in an observational learning situation, a stimulus is first shown to a demonstrator, and then the reaction of the demonstrator is presented to an observer. We could identify sequential brain-to-brain synchrony if the brain activity of the observer measured at a later time is coupled with that of the demonstrator. And despite the observation that brain-to-brain coupling measured during the learning procedure strongly links to learning outcomes, nearly all evidence in this area is purely correlational. Synchronicity between brain signals is only measured and correlated with learning. Scarcely any studies examine whether brain-to-brain coupling is simply epiphenomenal to interpersonal learning. That is, brain-to-brain coupling might emerge as a byproduct of intrinsic motoric and perceptual similarities between individuals during learning, or it might play a causative role in social learning mechanisms. To provide causal insights into the functional role of brain-to-brain coupling in learning, it's imperative to control or manipulate brain-to-brain coupling and observe its effects on learning. Recently, we addressed this open question by taking a novel approach. We use a multi-person transcranial alternating currents stimulation protocol to externally synchronize two brains, hence manipulating brain-to-brain coupling, and measure the resulting behavioral effects on social learning. And we found that the manipulation of brain-to-brain coupling led to better learning performance. Future studies are also encouraged to combine brain-to-brain coupling and machine learning. It would be fantastic if we could use brain data to decode learner and instructors' communicative behaviors during interaction. It's also promising to bring this novel hyperscanning technique into the real-world classroom, investigating instructor-learner interaction in a highly ecological valid setting. I'd like to thank Professor Philippe Pagnol, Camille, and Dr. Guillaume from Université Libre de Brussels, Belgium, and Professor Yi Hu from East China Normal University, China, for their valuable contributions in this project. Thank you for your attention. Any questions?
I would like to ask you if you could elaborate a little bit on how this research what you did, and this is also something related sorry, to what Ula is going also to present afterwards, whether you could see any bridge to bring your research to real classrooms, to analyze how different pedagogical approaches can be more or less effective, also within the conditions of the classroom, depending on the hours, depending on the pedagogies used. How do you see this could work?
Yeah, so I mean, this is of course very novel technique, and it's also a bit challenging to take this technique to the real world classroom. And you can imagine that for the real world teaching and learning, there might be some uncontrollable artifacts because our students and also and our teachers are moving all the time during teaching. However, the technique we are using here is called functional near-infrared spectroscopy, and this is a technique which is more tolerant of movement-related artifacts compared to some conventional techniques, for example, EEG. And it's also doable to measure the brain activity from learners and the instructors simultaneously during their the teaching and learning activities. And our previous work, as along with others' work, have already shown that the interpersonal brain synchrony between teacher and student, also between student and student, could act as a marker of their the effectiveness of teaching and learning outcome. So it could be ideal if we could collect their brain activity in the classroom as well,